Well, good evening. For you, it's probably Tuesday morning, but for me, it's Monday evening. First of all, I'm really sorry about the problems with today's lecture. I believe I have a plan that's going to work, and that is that I'm going to get you recordings for each lecture this week. I could do Thursday live, but the problem is that I'm going to give you a recording for Tuesday's lecture Wednesday, and not everyone may have it done to Thursday morning. So my plan is to get you recordings again for Monday, Tuesday, and Thursday's lecture. Also for each lecture, I'll break it in half. So this lecture I'm going to do right now would be the first half of Monday's lecture. It's going to take us through the end of the material for homework number 3. So if this is Tuesday morning for you, my recommendation would be to go through this lecture, write down the equations, the ideas, do the examples, and then after that, get cracking on getting homework number 3 done. I'm going to be getting the second part of the lecture up, and hopefully that will be a message we'll get you to Tuesday. All right, so about an hour, 15 minutes, something like that. Let's get going. So the rest of this, this lecture is on finishing off the Bernoulli equation applications that are in chapter 3. So once again, the idea of the Bernoulli equation, if we have a fluid moving from point 1 to point 2, there are 4 conditions. The flow needs to be incompressible, it needs to be steady, we need to be along a streamline. In fact, there's no viscous effects. If those 4 conditions are met, we're going to say that the mechanical energy of the fluid at the end is equal to the mechanical energy at the end. Pardon me, at the end is equal to that at the beginning. This equation you don't really need. It's conceptual, but it's worth thinking about. This is our first form of the Bernoulli equation that we talked about last week. Energy at the end, form 1, 2, 3, equals the energy at the beginning. Form 1, 2, 3. It's just like the pendulum stuff that you did in mechanics. Well, this is expressed in terms of energy per unit mass. We can also think of pressure as being a form of energy. And you can see that I got every term over here by just multiplying by rho. If I take an equation and multiply it by rho on both sides, that gives me a legitimate new equation. So this equation right here is the same equation as the first equation. These 2 equations are the same, just expressed in a different form. Hey, there's a few additional ideas. Sometimes when we fill in this equation, we're going to say P equals 0. More about that later. In addition, we need these 3 relationships, pardon me, 4 these relationships to do some more problem solving. And that looks very, very intimidating, but it's quite simple. So we're going to get to work and try to get both the equations, application of these equations, and the ideas behind it. One more quick note before we get going. You may look through the end of chapter 3 and say, wow, there are tons of different situations. But for this class, we're going to boil them down to 4. We want you to be able to do a problem where you know 5 out of the 6 different terms in the Bernoulli equation. We want you to understand what it means to say that a fluid is free somehow. We want to understand what stagnation means and how to use that with the Bernoulli equation. And finally, we want you to be able to do confined flow problems. So as you're thinking about getting ready for test 2, you should be comfortable with what all 4 of these things mean in the problem solving related to it. Very briefly, a little before we get started too, a little bit about the streamline concept. What is the streamline? Well, basically you can think of it as like a line the fluid follows. And we can many times write the Bernoulli equation from point 1 to point 2 on a line the fluid follows. So let's imagine we have a situation where I'm supposed to do some problem solving. We're supposed to find the pressure at this point here above the roof. That actually is not an uncommon calculation because many times fluids flow such that we get low pressure off a roof and it can lift a roof off. Pretty amazing thing. Okay, well, let's just go ahead and imagine what would, for these points I draw out here, what would the velocity vector look like? Velocity vector, remember a velocity vector shows the magnitude and the direction. So at this point, the wind might be going like this, and then here it might be going like this, and here like this, and now it's turning up a bit, and now it's turning up a bit, and now it's turning up a bit. Okay. If we imagine a particle going along that path, a question that gets asked in the book is, would all those velocity vectors be tangent to that line? And my intent was to draw it in such a way that it was. Every velocity vector is supposed to be tangent to that line. So it might be possible that we could identify this as point 1, and this is 0.2. Because all the velocity vectors on the line going from 1 to 2 are tangent, we can write it is a streamline, and we maybe could write the Bernoulli equation. On the other hand, if we tried to make this point right here like this, 1, and this point here, 2, would velocity vectors in a line connecting those 2 points, some sort of smooth curve collecting those 2 points, always be tangent? And no way. Here the velocity vectors would be like that. That's not tangent to that curve I just drew. I ask you on homework number 3 to read a little bit about the book's concept of a streamline. Good background idea to think about. So, first scenario, I'm just calling this 5 out of 6, where we know 5 out of 6 terms for the Bernoulli equation. So what I would encourage you to do is take a look at this picture. I don't think you need to write it down, but on a sheet of paper, hopefully taking notes, I would try to write the Bernoulli equation and confirm that you know 5 out of 6. Hey, there's 2 terms of the Bernoulli equation. There's one that starts as P2 over rho, and there's one that just starts with P2. Since the goal here actually is to solve for P2, I would start with the equation where the P doesn't have the rho underneath it. So go ahead and write that and confirm that you know 5 out of 6. Be thinking about how to solve it. So I bet you got it, but just running through it really quickly. There is the Bernoulli equation in the form that I was looking for. Let's go to the beginning. Do we know all 3 energy terms at the beginning? Okay. Well, P1, that was given over here. I know you can't see it all that well, but P1 is given there. 1/2 rho V1 squared, well, we can look up the density of glycerin, and we got the speeds, we got that. And then rho GZ1, well, that's going to be 0 because this is basically saying that at 1 we're at the ground level. So we got 3 out of 6. We got 3 out of 6. It's going to be easy if we get 5 out of 6. Okay, the potential energy term at 2, yes, we have that. We know it's at 15 feet. The kinetic energy at 2, yes, we've got that. It looks to me like what's going on here is this pipe is narrowing. And what happens with a liquid or an incompressible fluid when a pipe narrows is, well, it's got to fit through smaller areas, so it ends up speeding up. Anyway, so we have 1, 2, 3, 4, 5. We don't have the 6th term, so we can go ahead and solve for P2. So I'm going to really quickly get the numbers up there for each term. And I encourage you to do it yourself, and we're going to try to solve for P2. Okay, got a bit of information up there. Rho GZ10, that's obvious. 1/2 rho V1 squared, I'm getting 122 on my calculator. How about units? This is really, really important when you do this calculation here. So I got the units up there, density slug per foot cubed, V squared, foot squared per second squared. We can cancel out one of these feet, and we can group everything where we take the slug foot per second squared and get the numerator divided by a foot squared. And this is really helpful to know that a slug foot per second squared is a pound. So I get a pound per foot squared. So this number here is a pound per foot squared. Okay, let's start talking about P1. So there are 2 issues with this form of the Bernoulli equation when it comes to pressure. One is getting the units right, and the second is whether it's gauge or absolute. Gauge versus absolute. As long as we're consistent on the left side and the right side. Left side gauge, right side gauge, or left side absolute, right side absolute, we're good to go. Secondly, units. Hey, these 2 terms at the end usually calculate in BG units to give us pound per foot squared, but a lot of times the pressure is given in PSI, so this is 20 PSI up in the corner. So if I wrote down 122 here, I'm going to have to take that 20 and multiply and convert it to pound per foot squared. So 20 pound per inch squared multiplied by 144. I'm going to do that on my calculator really quickly. Should be able to do that in my head. Get a huge number, 2880. Okay, where those are all the numbers on the left side, those are probably right side, those are all pound per foot squared. Okay, why don't you see if you can go ahead and get the 2 terms over here, and I'm going to be doing it myself. Okay, so here's how my numbers work. For the elevation pressure, I got 1178.5. And for the kinetic energy pressure, sometimes called the dynamic pressure, I got 1098. Now that's easy enough to solve. So I'm going to do it myself. Hopefully my numbers are correct. I'm really sorry I did not have time to like do my Excel spreadsheet and make sure my numbers. But hey, you follow this and you have the idea of the problem solving. But bear with me for a second where I get the numbers up there. All right, finishing this off. So just did the algebra, and I got that P2 is 725. Pardon me. Yes, 725.5. Some things to do at the end when you do the Bernoulli equation. Think carefully about units. If it's pressure you're doing, is your answer gauge or absolute? And then finally, what kind of energy conversions take place? So first of all, units. These were all pound per foot squared. That number is pound per foot squared. I'll write that up there. You can probably imagine what's going to be asked for in problem solving. Many times here in the States, we do pressure in PSI. So we're going to convert that to PSI, and that involves dividing by 144. So I've got 5.04. I'm just going to round it off and call it 5 PSI. Okay. Hey, is that gauge or absolute? Well, going back to the original equation, this P1 that I filled in from the 20 PSI, not super clear on my problem statement, but P1 is 20 PSI, but in the picture, there's a gauge there. So you can probably assume that's gauge pressure. That's what we're going to assume. So if this is gauge pressure, what we solved from here would be gauge pressure. So this would be 5 PSI gauge. Okay. And then finally, probably the most important thing in some ways is to think about energy conversions. What type of energy was gained and what type of energy was lost from going from here to here? So going from 1 to 2, we gained potential energy. Okay, let's do the kinetic. Going from 1 to 2, it sped up, so we gained kinetic energy. Well, if mechanical energy is pressure energy plus kinetic plus potential, then if we gain both potential and kinetic, we must have lost pressure. And if you look at the numbers, we started at 20 PSI up here like this, and then we ended up at 5 PSI. So we lost pressure, and it kind of makes sense thinking about our energy concept. A quick aside before we get back to the Bernoulli equation. One thing we're supposed to be really good at in fluids is working with volume flow. So volume flow is things like gallons per minute, cubic meters per second, cubic feet per hour, etc. And there is an important equation that we need to be able to do. And that equation allows us, for example, in a case like this, where we have a duct, and the duct's a wide duct, it's a huge duct, it's 5 feet wide and it's 2 feet high. And we know the average speed that a fluid is moving through that duct. To get the volume flow rate, in this case, it'd be cubic feet per second. So maybe pause for a second and see if you can come up with that number. I'll be doing it myself. Okay, it turns out in this case, the answer is 80 cubic feet per second. If I go to any single point in that duct, every second, 80 cubic feet of this fluid, maybe it's air, is going to move past that point. And it's easy enough to come up with a derivation where you make sense of this. If you thought about, okay, like, let's take this fluid that's entering the duct right here like this, and let's imagine where it is 1 second later. Well, if it's going 8 feet per second, it's going to be 8 feet down the line. It's going to be down here 8 feet further down the line. That whole time, additional fluid is going to be in here. And so we could imagine a box of fluid here, and that entire box in the second has passed this entry point, okay? And that's what we want. We want to think about that when we get volume flow. Volume flow for a fluid at any point in a passageway is the volume that goes past that point per unit time. So without much saying, I mean, how did I get this 8 here? Well, then I just took 5 times 2 and I multiplied it by this speed. I took 10 and multiplied the speed, and what is 10? Well, that is the cross-sectional area. So it turns out that a good formula that we can use is the volume flow rate of a fluid is the average speed of the fluid times the cross-sectional area of the passageway. Very useful equation in fluids dynamics that you'll use all the time. Of course, it can be solved for anything else. Sometimes you're going to solve that equation for volume, for average speed. V is average speed in this equation. And you're going to do volume flow rate divided by cross-sectional area. And you'll even solve it for cross-sectional area. And that will turn out to be speed divided by, that will be equal to volume flow rate divided by speed. By the way, these sort of algebraic manipulations, a few of you got tripped up on that on quiz 1, something we want to be good at in this class. I know some students who have felt like, wow, I get tripped up on these very basic ratio stuff, end up using that triangle. And so the triangle is basically, if you have a ratio, V is Q over AC, I can put the V over here, I can put the Q over here, and I can put the cross-sectional area over there like that. And then there's that covering idea. Anything I want to solve for, I can cover, and then the triangle tells me what to do. If I want to get speed, I do Q over A. If I want to get Q, I do V times A. And if I want to do A, I get Q over V. Okay, we're going to use that equation quite a bit. So the next Bernoulli type problem involves what you might call the free fluid concept. The book has a section where they call it free jets, and that's the application. But there's a general concept to that of a free fluid, and we've already talked about that. So for like in a manometer, in a case like this, what's the pressure at the top of that manometer? Well, if this is open, it's going to be the same as atmospheric pressure. So we could sometimes say that this is a free surface and the pressure is at atmospheric pressure. Other applications, though, of this free fluid concept, the idea that the P is equal to the P atmosphere, or if we do our pressures in terms of gauge pressure, the pressure is basically equal to 0 if we're doing gauge pressure, because, well, if we are at atmospheric, we're 0 above atmospheric. Okay, how about this case right here? What if we had a balloon with a gas in it, and the pressure is going to be elevated many times inside a balloon? We squeeze some fluid in there. Okay, what if we prick that balloon? What's going to happen to the pressure of this fluid here? Well, you know that eventually it's going to spread out and reach atmospheric pressure. The idea, though, is actually, even in a case like that, any gas, maybe it's helium or whatever, that emerges reaches atmospheric pressure almost like that. And you can think about it, you need to do some experiments with a balloon where you prick a balloon and you pop a balloon in it. Like that, the pressure drops from an elevated pressure to a lower pressure. Okay, well, we can use that free fluid concept in a case like this, which may not sound like that interesting an engineering problem. What if we have a really tall vessel and we're trying to figure out, hey, how fast is the fluid going to come out? In this case, we're going to make our fluid H2O, all right? But this is a really practical question, actually, that people worked on for a long time. You know, like if someone's doing some wine brewing or doing some brewing and you have a huge vat and you want to empty it, well, it would be a very practical question to know, hey, when we have 10 feet of fluid, what gallon per minute is going to come out? You know, if you were trying to fill stuff or you were trying to empty this, what would the gallons per minute be? Hey, I'd like you to just write an equation and see if you can pick the correct form of the Bernoulli equation. And secondly, confirm that you have 5 out of 6. So go ahead and get started on that. By the way, before I got started, I should have said in addition, what you want to do is to try to imagine a streamline and see if you can identify a point 1 and a point 2 in the picture for which you're going to write the Bernoulli equation. We always need a point 1 and a point 2 for the Bernoulli equation. Okay, well, I'm going to make my point 1 up here at the top of the fluid and point 2 where the fluid emerges there. And I'm imagining the fluid, some sort of fluid that traversed this path would be going down and coming to this point over here like this. Okay. In fact, that could be a streamline with velocity vectors down, 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 velocity vector turning, the velocity vector being tangent to the path at every single point. And if I make this 1 and I make this 2, I do know 5 out of 6. Let's get that down, 5 out of 6. So I chose this form of the Bernoulli equation because there's less manipulation algebraically to get V2 by itself. If you chose the other form, it's going to work, no problem. Well, let's take a look. Do we know 5 out of 6? So first of all, let's go to the beginning point, okay? If I make this dotted line right here, the 0 level, then I know the Z1, at 1, that's 10 feet, so I know GZ1. Okay, what about V1 squared over 2? Hey guys, I didn't do a great job. I should have said this tank is really, really wide. And if this tank is really, really wide, but the outlet's only 2 inches, then this top is going to be hardly moving down at all when the fluid, which is water in this case, comes out of the bottom. So it is a reasonable assumption in this case to say that V1 is basically 0. Okay, how about P1 over rho?
I didn't give you a pressure one, but once again, it's that free surface idea. It's an open surface of the atmosphere. So P1 is equal to either 14.7 psi or 0. Okay, moving over to the other side of the equation. Okay. GZ2, well, I said that dashed line was 0, so we know that. V2 squared over 2, that's what we want to get V2. And then finally, what about P2? What about the pressure at this point when it emerges? Okay. Well, it turns out our intuition sometimes say that this would be at high pressure. It's coming out really fast. Turns out that it's exposed to the atmosphere. And so as soon as that water emerges from that pipe, it drops to 0. So going through our list really quickly, okay, we've got these terms over here, all three of those terms, and we have this term and this term. We just don't know V2 squared over 2. And it's actually looking pretty easy because if we say, I'm going to make P1 gauge pressure, it will be 0. Then P2 is going to be gauge pressure as well. So let me write the next line and see what it looks like. It's always helpful to cancel anything out that you can and make anything 0 that you can. Okay, so this one turns out super easy. We just get V2 squared over 2 is equal to GZ1. You can certainly fill in if you want to. What I would do maybe is do the algebra first and then plug and chug. I'm going to try that myself. Okay, well, here's the math, and what looked like a pretty complicated problem with some assumptions turns out pretty easy. So I moved over the 2 and took the square root, and V2 is the square root of 2GZ. G is 32.2, there's 10. I hope I did my calculator correctly. I got 25.4. What about kind of units? What kind of units are we getting? Well, G is feet per second squared. Z is feet. So this whole thing on over here on this side is foot squared per second squared, and we take the square root. So this is all going to be feet per second, which is what we want. Almost done. By the way, that is, first of all, that's really fast. We want to get the volume flow rate. So volume flow rate, let's see if we can pull out the equations we did in just a minute ago and get that right. So we want to get the volume flow coming out of this. We know the speed's coming out, so we can do volume flow is speed coming out times area. 25.4, and we got to get that area of the circle. Well, there's the 25.4 feet per second. Area of a circle, you'll notice in most engineering textbooks is pi d squared over 4. But we got to be consistent. So I need to take this 2-inch diameter at the outlet and make it into feet. And that's 1/6 of a foot. So let's crank through that and see how that works out in feet per second, feet cubed per second. All right, well, there's the math. Again, the diameter is 1/6 of a foot. So I need to be a little bit careful when I go through my computation. I got 0.554 cubic feet per second. That sounds small, but a good thing to remember is that a cubic foot contains quite a few gallons, like 7.5 gallons. So I'm just going to do that on my calculator really quickly. I'm going to multiply by 7.48. And I'm getting like 4 gallons per minute. So trying to visualize that. I mean, imagine a gallon milk jug and you're here filling. You got to have 4 of those ready for a minute that are coming out. All right. Hey, so 2 last things about it. First of all, we would like to think about the energy conversion between our spot 1 and our spot 2. And going from 1 to 2, there's no change in pressure. There's loss in potential, and there's gain in kinetic. So basically, we would say in this scenario, as the water flows down to this point, potential is converted into kinetic. Second thing is, are our assumptions met? So for example, is H2O incompressible? Yeah, basically that's true. Could this be steady flow? Someone might say, well, wait a minute, the water's level is going to go down, and then as a consequence, the dynamics are going to change. Very good observation. But just for a little bit, we can say basically, for a little period of time, we can say it's steady flow. So for a short period when the water height is 10 feet, it's steady flow. Is it inviscid? There's a really big problem. There probably are frictional or viscous effects as we go through here. And so this is a rough analysis that we'll need to fix up later in the semester. Well, the next type of Bernoulli equation gets us into, or problem gets into a very important concept when it comes to fluid flow, and that is the idea of stagnation. Basically, stagnation says that sometimes we have a fluid stream and the physical geometry, the obstructions, the other objects involved in the fluid cause some bit of the fluid to come to rest, even momentarily, to stagnate, to come to rest momentarily. Well, here's a problem that puts that thought process into work. Let's say we're trying to do a power washer. So we've got some sort of nozzle here that's connected to hosing. And maybe we've got like a fan or a compressor or something like that that creates high pressure. And then the fluid, the air, we're going to make it air in this problem, comes along. Okay. And when it hits right here like this surface that we're trying to maybe sand or something like that, we want to hit it at 20 psig. We want it to hit it and create high pressure here that's going to do something for us. So, hey, if we're designing this, maybe we would need to say, hey, what kind of velocity do we need coming out here and what kind of pressure coming out there? So we got two units that we're going to try to come up with. Hey, what kind of velocity do we need coming out of the nozzle? What kind of pressure? Well, before we do that, maybe we should think about defining a streamline and seeing what's going on. I'll work through that with you before we start doing the numbers. So over here is that wall, okay? And I have some fluid that comes along, that comes out here. This is the fluid that's coming out of the nozzle. So imagine this surface right here is the end of the nozzle. And I've got this fluid coming over here like this. And I'm just gonna get going. I'm gonna call that 1. Okay. By the way, I'm sorry, that was supposed to be horizontal. Well, that fluid's going to come along here like that, come along here like that. It's not going to blast it's through the way of the wall, and it's not going to just gob up on the wall. Air doesn't do that. It doesn't create a big gob here. So what actually happens? Well, some of this fluid ends up going here and turning upwards or left or right, depending on how we're looking at it, and some goes downwards. Okay, but you can see basically that some fluid is actually going to, we could think of a very infinitesimal stream of fluid that basically over here comes to rest. This fluid above it turns upward, this fluid below it turns downward, but we can have this fluid that basically comes to rest. So we could call that stagnation. And that's what we're interested in. We're interested at the point right on the wall where the fluid is directed. And so we're going to call this point right here our point 2. Okay, so considering that we are, by the way, our ultimate goal is going to get V, to get V, and that would be at the outlet. Let's see if you can write the Bernoulli equation and check that you have 5 out of 6. All right, so there we go. I chose this form of the Bernoulli equation. If you chose the other one, it's going to work. But hey, do we have 5 out of 6 of these terms that will allow us to solve? So let's just go ahead and take a look at the endpoint here. Well, let's take a look at the, let's take a look at the elevation terms. This was my streamline, this black point here like this. Comes out of the nozzle, that bit of air that goes straight, hits into that wall essentially. Okay, so we're neither moving up or down. So basically we can say there's no change in elevation energy. So we can take 6 terms, cross out those 2 and make it 4. We're getting closer. Okay, how about at the end, the pressure? Do we know the pressure? Well, absolutely, that's what we're saying. We want it to turn out to be 22 psig, so we know P2. The density we can get from the tables. Okay, how about 1/2 V2 squared over 2? What is this velocity right here? Well, that is the idea that we're getting stagnation. We can identify a fluid streamline for which some bit of fluid actually comes to rest. So this term right here, gone, that's 0. Hey, this is looking a lot easier. You don't need to, but I'm going to rewrite it with the updated information. All right, so there's the updated equation with the 0 terms eliminated. We want to solve for V1. We want to solve for the speed that the air needs to come out of the nozzle. And I also said solve for P1. So that's looking pretty tough. You know, it doesn't seem like we have enough information. But once again, what is P1? What is the pressure of that air when it emerges from the nozzle? And it's exposed to the atmosphere, it's free. So P1 is actually also equal to 0, and we can eliminate that. And now we can see that we can solve this for V1. So look, when I first saw this, when I was doing fluids, I thought that was really, really strange. When I think like a pressure washer or something like that, I'm trying to like wash a sidewalk with a pressure washer, holding this hose, I would think the fluid that comes out would be under really high pressure, and that's going to create the pressure. But that's at the sidewalk. But that's not it. What creates the pressure as it comes out, it's going really, really fast. And then when it hits the sidewalk, if this fluid comes down, that's the sidewalk, the whiteboard, the sidewalk, that velocity speed, that speed is converted into pressure. So for a pressure washer of some sort, what you really want to do is make it so that when it comes out of the nozzle, it's really high speed. And then with stagnation, that high speed can convert to pressure. Hey, let's do the math and actually come up with what that speed needs to be for air. I think it's going to be really large in this case. So getting going on it, I did the algebra, and V1 squared would be equal to 2P2 over rho. P2 we wanted to be 20, and there's the density of air. By the way, in a problem like this on a test, the numbers would be given, so you can know whether you need to do the ideal gas law, or in this case, we can assume that you're allowed to pull the number from those basic easy tables. All right, hey, trying to finish it off, there's clearly a problem. We've got mixed units, feet cubed and inches squared. I would convert this inches squared to foot squared. I'm going to try that on a board and see if we can finish off the units and get it right. All right, so taking a look at it, man, it turns out to be a huge number on my calculator. But that's V1 squared. So then we would have one more step and we would do the square root. We're still going to get a really large number. 1555, maybe 1556. So that's 1,556 down at the bottom. Hey, how about the units? Carry through that. I'll just do that little bit of work here on the side. So basically we did P over rho. So P we made into pound per foot squared, and rho is slug per foot cubed. That simplifies to a pound foot per slug. And it turns out, we talked about this earlier, a foot squared per second squared and a foot pound per slug are the same. So at this step right here, when we had this huge number, that was foot squared per second squared. Okay, and so we end up getting feet per second here, which is what we want. Sorry about my writing, but there's the answer. Okay, so hey, if you want to create a pressure washer that's going to create 20 psig at the wall, man, it's really going to come out have to be at fast speed if it is air. And that should make sense in a way. Air, we get air going really fast, and it does work for cleaning with compressed air, but it doesn't actually create a lot of high pressure, and that's because air has low density. And as the last step on this problem, what kind of conversion took place? Well, we have a conversion from kinetic energy to pressure energy. And so that kinetic energy, the air is stagnating, and we're getting pressure as a result. Okay, so the last Bernoulli thing we're going to do is confine flows. But before we do that, it's helpful if we know a little bit about mass flow rate. Very important fluid concept. So mass flow rate is usually for a point in space, like say the inside of a pipe, and it would be per unit time how much mass actually passes that point. The symbol that's used in your book and almost all books for mass flow rate is m dot, m for mass and dot because it's rate. Okay, what about units? SI units for mass flow rate. How much mass flows past that per unit time? We're going to do kilograms per second almost always. Okay, how about BG units, British gravitational units for mass flow rate? How much mass passes that point at unit time? Okay, well that is going to be slugs per second. There also is the EE system, which would turn out to be pound mass per second, but we're mostly going to do SI and we're going to do BG. So first of all, we need to know what M dot is. We need to know its units. And it turns out there's some really fundamental calculation we need to do. And that is many times out in the field, fluid flow rates are given as volumetric flow rates, like feet cubed per second or gallons per minute. And we as engineers want to take that feet cubed per second or that volume flow rate and convert it into mass flow rate. So what would I multiply cubic feet per second by to make it in slugs per second? Well, that would be, I would need to get rid of the cubic feet. So I would try to come up with a relationship that has cubic feet in the denominator. And I want slugs in the numerator so that the units work out, that I end up getting slugs per second over here. Hey, what kind of term is that about a fluid? The number of slugs the fluid has per cubic foot. That is fluid density. So it looks like what we can do is we can take volume flow rate and multiply it by density to get mass flow rate. And that's exactly right. That is our next equation for the semester. So basically, I just said that we can get mass flow rate for a flow by doing the density times the volumetric flow rate. Earlier, we said the volumetric flow rate was average fluid speed times cross-sectional area. So of course, we can have another flow problem, another equation that says that m dot is equal to rho times VA, where A is the cross-sectional area. And that is another very useful equation for mass flow rate.
And once you understand the mass flow rate concept, we can discuss continuity. So continuity is an equation that results from thinking about steady situations. So I'd just like you to take a look at this. Could that be steady? I've got a pipe, and over on the left, 4 kilograms per minute is flowing in. And on the right, 2 kilograms per minute is flowing out. How long could that go on? And the answer is hardly any time at all, because if we have 4 in and 2 out, every minute we have a 2 being gained. There's actually 2 staying in there somehow. That pipe is going to burst in no time. So if we have steady flow, what that means is that flow in is equal to flow out, and it's expressed in terms of mass. And let's write that in equation form. Okay, we're going to write pretty fast to get going, but continuity is for some sort of pipe or some sort of system where we have an inlet and an outlet, or a first point and a last point. It's got to be true, if it's steady, that the mass that flows in exactly has to be balanced by the mass that flows out. So there's our continuity equation. Well, of course, we could write it in various forms. We could also say that rho 1 times Q1 has to be equal to rho 2 times Q2, because m dot is equal to rho times Q. And of course, these could be equal to rho VA1 is equal to rho VA2. And for some of you, this may look pretty trivial, but it turns out it can be very useful for problem solving, for figuring out a lot of stuff. And our Bernoulli equation is steady, so we're going to be able to write that equation. It's even better for Bernoulli. If it's incompressible, and I'm just going to abbreviate that as IC, just because I'm running out of time a bit, but you can write out incompressible. How does this equation change if a fluid's incompressible? Well, incompressible means it doesn't change, essentially it doesn't change density. So if these two densities are the same, we could say V1A1 is equal to V2A2. Okay, and all these equations are important to be able to work with. Let's practice them a bit. All right, last example of the day. Let's see if we can put it all together. So we have a pipe with a piping system with a restriction. We have some H2O going along here at 4 meters per second. That's actually pretty fast. 4 meters is like 12 feet per second. And it's an 8 centimeter diameter pipe. At this point right here, the pressure reading is 20 kPa. And so that would be 20 kPa above atmospheric. Then there's this narrowing, and we get down to a 4 centimeter diameter. And we're wondering what the pressure is at that point. Okay, let's put it all together. We're solving for pressure, so it'd probably be good to use the pressure form of the Bernoulli equation. Let's write the equation, identify a point 1 and point 2, and see if we can essentially have get 5 out of 6, or narrow it down so we only have one unknown. Okay, there we go. So I recommend using this form of the Bernoulli equation. I have yet to identify a point 1 and 2 in my diagram. I encourage you to do that. And then in addition, let's see if we can make this equation simpler. So first of all, point 1 and point 2. So I think the pressures kind of dictate what to make point 1 and point 2. I know a pressure over here before the restriction, so that's my point 1. And 2 is where I want to know the pressure, that's the outlet. Okay, we can imagine there being streamlines of flow going from 1 to 2, where the velocity vectors would be tangent everywhere to those red lines. And that's good enough. Let's see if we can now simplify this equation. A good first thing to think about is, what about the elevation terms? It might look, if I say make my first point 1 here and the second point 2 on that streamline, we've gone down a little bit.
Or if conversely, I made my first point down below here and my second point up there, we've gone up a little bit. Well, it turns out that these distances, remember the pipe diameters were like centimeters, are virtually nothing. So we can say there's hardly any change in elevation, so we can get rid of those two terms. All right, let's see if we know anything else then. It turns out that we know V1, so we've got that, okay? We've got P1, we've got that. We want to solve for P2, and there's the problem. We don't know V2. But I claim that we do, because we know the continuity equation. So continuity equation would be that basically m dot 2 is equal to m dot 1. We could write rho VA2 is equal to rho VA1. The densities cancel because we assume that it's incompressible and density is a constant. So we can say V2A2 is equal to V1A1. Okay, and that's how we're going to get V2. I would like you to try it a bit yourself, but I encourage you to do it algebraically first, and I'm going to get started on that in just a second. If you can do that yourself, great. At a minimum, think, hey, what does he mean by doing it algebraically? Okay, here's what I meant by doing it algebraically. I just filled in symbols and to solve for V2. So I got V2 is V1 times A1 over A2, but A1 is pi D1 squared over 4, and A2 is pi D squared over 4. So, hey, for a minimum, we can eliminate the pi's and the 4's. I'm going to do that quickly. Okay, now it's not so bad. So I'm going to get V2 is V1 times D1 squared over D2 squared. And I could start fooling around my units, but that should be easy enough to do. If we think about it, D1 was in centimeters, 8 centimeters. D2 is in 4 centimeters. Those centimeters are going to cancel out, so I don't need to actually think about converting them to meters. They'll just go away. And so this is going to be V1, which was 4 meters per second, times 8 squared over 4 squared. 8, so 64 over 16, which is 4. And so we're going to get this is equal to 16 meters per second. So there's my V2. I've got it. I worked it out. And it should make sense. Once again, we have some fluid that's trying to go through a smaller passage, and it ends up going faster. And that's been observed again and again in nature. If you try to take water or something like that and fit it through a narrow passage, you get a rapids. You get it going really fast. All right, let's finish it off now that we have V2. Let's fill in the Bernoulli equation and see if we can solve for P2. Hey, sometimes the book does a lot of algebra before they fill in, and you can certainly follow what they do. I sometimes in class will tend to do an intermediate, do a bit of algebra. So I solved this equation for P2. That's what I wanted to do, and I got this equation right here. I noticed that there's a 1/2 rho in these two equations, so I factored it out. So maybe I can save myself a little bit of computation. And let's finish it off. I'm going to use 1,000 for rho since it's water. That's the nice easy number in SI units. Well, when I plugged in all the numbers for this computation over here, that 20 is P1. And this negative 24,000 I got when I did 1/2 rho V1 squared minus V2 squared. Hey, how about that negative 24,000? What kind of units is it? So it comes from rho V squared. There's rho. There's V squared. That's one I really encourage you to work on as you do as the homework. One way you can see it is I can eliminate one of the meters, and I end up getting kilogram meter second squared per meter squared. All this stuff is a Newton. So this stuff is a Newton per meter squared, which is a Pascal. So that negative 24,000 is a Pascal right there like that. This was kilopascals, so I should probably take that negative 24,000 pascals and convert it into kilopascals, so it would be negative 24 kPa. And we're almost done. So I have 20 kPa minus 24 kPa. I get negative 4 kPa for the pressure at this point 2, which was what we were looking for. So first of all, does that even make a sense? Wait a minute, negative pressure? Well, that's gauge pressure, so that means we're 4 kPa below atmospheric pressure. Secondly, what's happening energy-wise? Always want to think about the conversions. So going from here to here, no change in potential. Okay, going from here to here, definitely a change in kinetic. The kinetic increased. Well, if one form of energy increases, another form has to decrease to compensate. And that's the pressure energy. The pressure energy has decreased from 20 and gone down to -4. And so what we say in a case like that is, hey, pressure has actually been converted to kinetic energy. And that's actually what's going on. The fluid needs to speed up to get through that narrow passageway. Well, speeding up involves acceleration. Where does the energy from acceleration come from? From the pressure. The pressure is able to push and give it that speed, but as a consequence, the pressure ends. Hey, one last thing, we're done. So last thing, in this form of the Bernoulli equation, where that expression is written this way, we have three terms, and sometimes those are called pressure terms. And we sometimes work with those and have different terminology that's thrown out there. So let's go through them one by one. Okay. Where in this equation is the elevation pressure? Which term asks is elevation? And that's that one there, that's elevation pressure. What about dynamic pressure? We talked about that before. Where is that in this lineup right here? And the dynamic pressure is that one right there. Okay, what about the static pressure? That's the pressure that would exist even if the fluid was not moving. And that's that term right there. So that's static pressure. Okay, stagnation pressure. Well, we have the idea that if a fluid stagnates, its kinetic energy or dynamic term actually becomes pressure. So this combination right here, those two right there for a fluid, is sometimes called the stagnation pressure. You can combine the static pressure and the dynamic pressure to get the pressure the fluid is going to create if it stagnates, say like against a wall. And then finally, there's the total pressure, and that's the combination of all three. All right. Again, I am sorry about this morning that I wasn't ready to go. This is the first half of Monday's lecture. My recommendation, get through this, get this done, jump in, make your goal to finish off homework number 3. More coming from me soon. Please feel free to contact me by email. I'll do the best to get back to you and keep this thing going.